This is a video on how satellites and zero gravity weightlessness. Now let me explain to you something. When you have a satellite in orbit like this, they need enough speed to stay in orbit. If they don't have enough speed, they'll crash to the floor. But at these insanely high speeds, how come they don't just fly off into space? The thing keeping them from doing this is the gravity of Earth, right? So that means they're always getting pulled in the centripetal direction by gravity, which means that they're always falling. That's what being in orbit is. It means always falling toward Earth, but the tangential speed of the satellite keeps it from hitting Earth. Now, the formula for the speed you need to stay in orbit as a satellite is V equals the gravitational constant times the mass of Earth divided by radius, and this is also under the square root. Here's something interesting. This formula doesn't involve the mass of the satellite, only the mass of Earth. So that means no matter how heavy your satellite is, it will move at the same velocity as any other satellite, no matter how heavy. So let's go through a fun problem. You are a scientist from the future, and your task is to build an advanced space station. And they say it needs to hover above the same spot on the equator. So let's say this is Earth. This is the equator of Earth. Your satellite has to hover above the same spot on Earth the whole time. And this is a crucial concept in satellite mechanics. The orbital period of the satellite has to match the rotation of the Earth. Now here's the questions I'll give you. What altitude does your satellite need to stay at in order to remain in sync? The second question, what's the orbital speed required to stay in sync? And the last question, compare the speed to a low orbit satellite that is 200 kilometers above the Earth's surface. I'll put this aside so that we have some space to solve. Let's start with altitude. Now here's what we know. We know the mass of Earth because we can Google that. We know the radius of Earth because we can Google that. And we know the gravitational constant. I'll write it out, but I'll speed it up because they're big numbers. We also know the orbital period. The orbital period of our satellite is 24 hours, which is 86,400 seconds. Now, since our satellite is undergoing circular motion, the gravity is providing all of the centripetal force, which means that the force of gravity is equal to the centripetal force. As we know from Newton's law of gravitation, the force of gravity is equal to G times N1 times M2 divided by radius squared. And centripetal force is given by the formula mv squared over radius. Let's say mass 1 is the mass of the Earth. That means this would be the mass of the satellite. We can cancel these out. And because we know velocity is equal to circumference divided by time, then we end up with this formula. 2 pi r divided by t squared divided by radius. If you're feeling a little lost and you're saying things like, how do you know how to do this? How do you know which things to cancel, which things to solve? Well, I've said this before, but it really just comes with time and experience. When you solve a lot more physics problems, you'll develop a strong intuition for what you should do next. Here, I'll try and explain the logic. We're trying to find a formula for the radius, because the radius is this distance, the altitude. Now, if you want extra practice, go check the description. Let's solve for radius, which gives us radius cubed equals a bunch of stuff here divided by a bunch of stuff like this. That's our formula. We have all the values. We have this, we have this, we have the time, and then all we would have to do is plug. Now, I'm not going to go ahead and plug for the answers because there's a bajillion numbers here, but we do have everything we needed to do if we wanted the radius. Now let's find the orbital speed required for our satellite to stay up, but not just up, but also in sync with Earth's rotation. I explained to you a formula from the start of the video, which is V equals G times the mass of Earth divided by radius. This is the formula for orbital speed. When you plug in our values with a calculator, you get roughly 3071 meters per second. That's how fast our satellite is moving. And if you went and Googled it, then you would see around 3 kilometers per second. So yeah, our answer is right. That's the orbital speed done. Let's compare the speed of our satellite to a low Earth orbit satellite. So remember this formula, right? For orbital speed. To find the speed of our low Earth orbit satellite, we also need the radius. Let's draw our satellite real quick. Let's say it follows this path, lower. The distance from here to the center of Earth is his orbital radius. That means we can add the radius of Earth with 200,000 meters, which is how high he is above the surface, which is something like 6,571,000 meters. When you plug this into this formula, you plug in the gravitational constant and the mass of Earth, you end up with roughly 7.8 kilometers per second. Now, what was our main satellite speed? It was 3 kilometers per second, right? That's half the speed of the low Earth orbit satellite. This is proof of a concept I think I explained in another video, which is when it comes to centripetal force and centripetal acceleration, the bigger the radius, the slower your thing will go, because centripetal acceleration is smaller. So the further away you are from Earth, the slower you will travel in orbit. Let me teach you about weightlessness now. So when you see people in the ISS, the International Space Station, you think they have zero weight, zero gravity. They're weightless. However, being weightless is not the same as an absence of gravity. People on the ISS actually experience about 90% of the Earth's gravitational pull. On the surface of Earth, down here, the weight you feel, when you feel weight, it's actually the normal force. That's because the floor is pushing the normal force on you. On the ISS, as it flies through space in orbit of Earth, everything is falling at the same speed. So nothing gets the chance to push on you because everything's falling together. That's why you can float around, because you're in free fall technically. Now, why do you feel weightless? Let me try and give you another example. When you go on an elevator and the elevator goes down, the normal force pushing back on you gets weaker as you accelerate down. And I went through this in another video as well. But that's basically what's happening on the ISS. Because you're always falling, you're always accelerating down, you're kind of weightless in a way. For every topic I cover, I like to create a free cheat sheet. And I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.